thank you everyone for coming. I guess it's the first edition of the Ekumen R&D Seminar series. Today, Professor Rosati Papini and Dr. Piccinini will be talking about NNodely, an open framework for model structure neural networks in robotics. Gastone is an associate professor in advanced control systems applied to autonomous driving and ADAS at the Department of Industrial Engineering of the University of Trento, Italy. He received a master's summa cum laude in automation engineering from the University of Pisa in 2012 and earned his PhD in emerging digital technologies from the Santa Ana School of Advanced Studies in 2016. He's also the co-founder of Cheers SRL, a spin-out company from the University of Pisa, specializing in renewable energy and ICT solutions. With over 10 years of experience in mechanics and control systems, he has recently focused on applying machine learning techniques to model and control mechanical systems. Thank you, Gastone, for being here.
Thank you very much. Thank you very much.
On the other hand, Mattia Piccinini is a TUM Global Post-doctoral Fellow at the Professorship of Autonomous Vehicle Systems at the Technical University of Munich in Germany, TUM. He received a master's summa cum laude in mechatronics engineering and a PhD, also summa cum laude, in autonomous systems from the University of Trento in Italy in 2019 and 2024, respectively. His PhD thesis obtained the 2025 Best Dissertation Award from the IEEE Intelligent Transportation System Society. His research lies at the intersection of machine learning, physics-based modeling, and control for mobile robotics and autonomous vehicles. Again, thank you, Mattia. Thank you for meeting me at ICRA. Thank you for being here today.
Of course, yeah, it's a pleasure.
For a very brief update on how the dynamic of this talk is going to work, for the next hour and 15 minutes, hour and 20 minutes, Gastone and Mattia will be talking. If you have questions, you can go bottom right to the 9 dots in Google Meet, look for the QA item, and you can add your questions. Everyone can vote up everyone else's questions, and for sure at the end of the presentation, but also at Gastone's or Mattia's discretion throughout the presentation, they will answer these questions. So without much further ado, Gastone, Mattia, the floor is yours.
Thank you very much, Michel, for this nice, very complete presentation of me and Mattia. So it was very a pleasure to be here to present our work. I hope that we will enjoy the presentation. So I will start today talking about NNodely, an open framework for model structural neural network in robotics. So I hope that we will enjoy the presentation. So one moment. Okay. So first of all, we will start with a brief. Also, I introduced Mattia that we will jump me and you and him during the presentation. So I will start giving you a short introduction, motivation, something beyond the black box neural networks. Then we will show you the physics guide learning, and then we will deep in the NNodely framework, the model structure neural network, the framework itself, and some use cases. In particular, we will focus on vehicle, but because we know that you are mostly interested on that. And finally, we will show you some conclusions. So we start to motivation. Why we want to use model structure neural network? Why we will go beyond the black box structure? So first of all, I want to introduce the basic perceptron. The perceptron was introduced by Rosenblatt in 1958, and is based on a main product, a summation, weighted summation of inputs plus a bias, and then you have a nonlinear function. Commonly, it can be a sigmoid, can be a ReLU function. But of course, this simple structure that was introduced by Rosenblatt can only do something. But I mean, this was based on the idea of how a neuron in the brain was working, but of course, it can't do everything. You know? So it's just a multi-input function with a single output, but you can do something more. How you can do more? You can put in a chain these perceptrons, creating a multi-layer perceptron that can have multi-hidden layers. So you have a list of inputs, then you have one or more layers, and then you have an output layer. there is a fundamental theorem that is called the universal approximation theorem that is say that a multi-layer perception with one single hidden layer, so you think that it can be a very huge, long list number of hidden layers, but in one single level, that can approximate any continuous function. But this is really in theory. So in theory, can approximate any continuous function, but this is only in theory, because in reality there is a lot of problem to train this kind of network. First of all, you can have the problem of data hungry. So you may need many data to train this kind of network. You have pure generalization, because you can fit, you can cover all the space of your inputs, and then also is a black box. Also, during the training, you can have many problems to go and back and find the global minima of this function. So at the end, we see that is not only better if you put many layers, so creating what is called the deep network, because the deep network is always more flexible to go and find the global minima. But not only, you can also structure the network. I want to show you just a very simple example of what can be done just structuring a little bit the neural network. I open the playground. I hope that you can see it. Do you see it? Okay. Okay, so this is a very simple playground that was built by Google to explain how a neural network works. Here you have a two cluster of points, blue dot and orange dot. And in this case, we have two hidden layers here, okay, with 4 neurons and 2 neurons. So I start the training, and the network is able really fast to get a convergence and get the global minima, because this is the global minima. I divided all the blue dots and the orange dots. But if I create a different cluster, a little bit more complex, and I try to fit this data using this simple network, commonly the network struggles a lot to find the minima, and is stuck in a single local minima. Also, if I including some additional layers and I include other neuron each level, may I can find a solution, may not, and you can see that commonly the network struggle a lot to find a solution. May will converge a good local minima, may not. Okay, so you see that it's not a very nice fitting in this case. But just if instead I remove all these hidden layers, I give only one single layer here, but add one symbol information that is related to the structure of my input. So I see that my input will follow some sinusoidal information, have some sinusoidal information. In this case, the network commonly is able, yeah, you see, okay, in this case is able to cluster pretty well the data. So now we get a very good fitting, okay, not amazing, but still we use just 4 neurons in this case, but we already get a very good result. And this is possible thanks to this simple information. We have some knowledge. We say that the inputs may follow a sinusoidal, have some sinusoidal pattern, and we put this information in our network. So the network can be computed, the sign of x of the sign of x1 or x2, or just embedding, or just pre-computing the sign and the sign of the input before passing to the network. Are two different ways to structure the data or the network. So in this case, this is already true. So what I say, okay, it's important to structure the network. And there is already some very nice result in the literature. If you think about computer vision, for example, convolutional neural network is one of this amazing example of structuring the network, because what we does the convolutional neural network is try to embedding the concept of spatial invariant. So the network, the object that you are trying to recognize doesn't matter the position in the image. So this information is embedded in the structure of the network, and for this reason, the convolutional neural network get much more high result when they try to recognize objects. This is one example of computer vision. Long short-term memory is another example of structuring the network. So it's not anymore a fully connected just random layer, but you are start to build, to construct specific layers. And finally, I think that is fundamental to say, now ChatGPT, that is one of the amazing results in neural networks, was able to reach this result thanks to transformers. And transformers are specific layer that is called self-attention, that is able to find the correlation between words in a phrase, and this was able to reach a very amazing result in neurocomputation. So this result was possible thanks to the idea of structuring the layers. So we have an example in computer vision, in speech recognition, in natural language processing. So can we advise neural network architecture to model and control physical systems? So we can do the same for model and control vehicle, for model and control physical system. This is the idea. So now we are talking about the physical guided. So there were some example of physical structure, but we can explode this possible way to structure the network in different ways. I will explain more in detail what is the meaning. So first of all, you can embed the physics, just curate your data. Okay, so you can, for example, transform your data from one space to another space to help the network to learn. This is already something where you put your knowledge, your physical understanding of the problem inside the data. Okay, you are rearranging the data in another way. This is one possible way. The second way is structure the loss function. So you say, okay, you want to minimize this function, and when you decide what the function the network will follow for minimizing the problem will follow what you think that is more important. And we try, for example, you will see next some example of loss function that are structured. And finally, what we will focus also using Model I is the internal structure of the network. So you can structure the input, you can structure the logs, but also you can structure the specific layer inside the network. So one example of structuring the loss function can be the physics-informed neural networks that are called pins. So the pins are typical neural structure, but they are mainly focused on the structure of the loss function. What is the idea of pins? The idea is data-driven solution or discovery of complex PDA. So the objective of this physics-informed, of this neural network, is try to minimize, integrate a complex partial differential equation. In this case, what they are doing, they structure the loss function. Thanks to this idea, they can integrate the partial differential equation, finding the solution in time. And these are very interesting results, and these go in the direction to try to put knowledge, to put physics inside the network. In this case, we'll focus only on structure of the loss function, but we can do, and we will show you how we can do in a different way. So, of course, the pro of this approach, I learned the solution of the PDA, using a small training set, accelerate the solution of complex system. The example in this case was fluid dynamics, Navier-Stokes, quantum mechanics, solid mechanics, reaction diffusion. Of course, this approach can't be used for control real physical system, but can be used only for integrating partial differential equations to find the solution of partial differential equation. There are some approaches that are based on pins that are mainly are called Hamiltonian network, Lagrangian networks. Also, there there is some network that are based on Pontryagin principle, but all these approaches are based to structure the loss function. The neural network itself will remain a fully connected layer in multi-perceptron layers with many layers, but you don't need, using this approach, you are not structuring the layers. You are only structuring the loss function. So if we go back to the slide before, so where we are showing the possibility of structuring the input, the architecture, and the loss function, we will want to show you that the internal structure that we are designing to build our network is the model structure neural network. Then we will show you a very nice example of model structure neural network. And I can say that Model I is focused to all the levels. So we help to structure the input, to structure the loss function, but also to, in particular, structure the internal structure of the neural network. So we will focus on all three, but in particular, the internal structure. So now we will present the Model I. So Mattia, if you want to go ahead from here.
So indeed, we can continue from what Gastone indeed explained, and now we go a little bit more in detail about this last approach, about the approach of structuring the internal architecture by means of model structured neural networks, in which indeed the idea is to embed some prior knowledge, some domain-specific or physics-based knowledge inside the neural network internal architecture. And we do so normally by starting from a physics-based model or from a model we know, for example, an analytical one, and we neuralize its internal architecture. And of course, the purposes can be many, can be modeling, control, estimation of physics systems, including, of course, robots. And let me give you an example, an introductory example, in which we want to learn actually the longitudinal dynamics of a vehicle. So in this case, our input is the pedal that can be throttle or brake pedal, if positive or negative, and the vehicle speed, Vx, and we want to estimate the longitudinal vehicle acceleration, Ax. So of course, one can build a naive multi-layer perceptron, right, in which Ax is simply the output of a black box multi-layer perceptron of pedal and velocity. Of course, one can do that. Is this the best solution? Probably not, because actually we know something about the vehicle dynamics that we can incorporate inside our neural network. And so let's start from what we know. Let's start from the Newton equations that tells us that the acceleration is the sum of the external forces divided by the vehicle mass. And let's expand this. So sum of external forces means longitudinal forces at the front axle, longitudinal forces at the rear axle, and aerodynamic drag. Okay, and this is analytical. This is an analytical relation, but still it can be difficult to expand further because we don't know a priori the relation between the pedal and the forces and the longitudinal forces. This relation can depend indeed on saturation of tire forces, on powertrain dynamics, on braking dynamics. So it can be hard to model everything analytically. And so let's build the first neural prototype of this implementation of this analytical version. So we have a first branch that processes the squared of the vehicle velocity and tries to generalize the aerodynamic drag relation with a small network. And then we have the second and third branch, which instead estimate the longitudinal forces at the rear and front axle, and that neuralize this relation between the pedal P and the forces by means of some neural networks which we can define. And still notice that we are preserving some principles like the superposition of forces given by the Newton law. And it turns out, okay, here we were using the instantaneous pedal value. We can do more by using actually a past window of pedal values. In this case, it turns out this helps in learning, especially the transient response of the system. And in this implementation, actually, these layers can be interpreted as fully connected layers on one side, or as layers that learn somehow the finite impulse response of the system. So that learn indeed the response of the system based on a previous input, on a previous history of its inputs. And what happens, okay, then we can complicate the system further. For example, we have an additional input that is the gear, okay, so first, second, third gear of the car. What happens if we have it? It's a discrete variable, but we can still build, for example, neurofuzzy models, local models, to actually learn the vehicle dynamics for each gear independently. And so we can expand it as indeed the combination of local models, of local branches, each of which is active in a certain gear, so first, second, third gear, etc., by means of these activation functions phi, which can have a generic shape for different applications. And indeed, we can complicate them further. We can have, of course, the contribution of the lateral dynamics on the longitudinal dynamics. So we know how the lateral dynamics actually enters the Newton law, okay, by means of this additional term, where this is the lateral forces multiplied by the sine of the steering angle. And we can neuralize. This is an analytical relation, but we can neuralize it. Again, for example, using a neurofuzzy model that estimates the lateral forces based on a past window of lateral accelerations. And we know the lateral dynamics actually changes as a function of the vehicle velocity. So the vehicle responds in different ways if we're driving slowly or at fast speed or at high speeds. And so we can indeed have a part of the network that estimates the lateral forces multiplied by a certain function of the steering angle that can still be using the sine function, and an additional small network to learn maybe some additional static nonlinearities in the steering mechanism. So this is an example of how we can incorporate some prior knowledge into a neural network. And so to try to generalize these principles that we mentioned here, some examples of principles we can embed inside our model structure networks are indeed the superposition of forces. So the thing that different forces behave in an additive way with respect to the on the resulting dynamics. We can treat indeed the discrete time system dynamics. We can treat it with finite impulse response layers, the ones we were mentioning before. So in which the output of the system at a time step n can be expressed by a linear combination, linear or nonlinear combination of its inputs, of a past history of its inputs, thus learning the indeed the finite impulse response. We could even model it as an infinite impulse response, depending on our modeling necessities. And in this case, the output at a certain time step also depends on the previous outputs, previous inputs and previous outputs. So in our case, we could actually think that we can feed back our acceleration and reuse it to improve its estimate. So reuse it as inputs and process it to improve the output at the next time step. For example, we could integrate this longitudinal acceleration to estimate the longitudinal velocity that then is reused as part of the inputs. And so this is indeed things that we can do to embed physical principles. When we have unknown nonlinearities, like in the example before, we can address them with neurofuzzy local models, as we've shown before. So for example, the longitudinal forces can be expressed as a combination of past brake pedal and throttle pedal values. We can have scheduling variables like the gears or like the vehicle velocity that change the vehicle dynamics or the dynamics of the system. And we can be very general here. We can have other additional input and output functions to further process our local model variables. And what also we try to do is we give the flexibility to define custom functions for ad hoc neuralizations to encode and to try to capture the residuals of what we cannot model analytically. We have the capability to embed the concept of time inside the neural network. We've seen it with the possibility to use past windows of inputs in our system. And we also have something we didn't see here, but we will see in the applications later, the possibility of defining very custom recursive relations, recursive networks. So we can actually feed back any part. We can actually make a loop with each variable inside the system. Each part of the network can be used to build the recursive relations in a flexible way. And so with this, we've given some examples of physical principles to be encoded in model structured neural networks. I will give the word back to Gastone to continue with the NNodely framework.
So what are the main aims of this network? Because in principle, you can do what you saw before in that network using standard PyTorch, TensorFlow, JAX, what you want. But of course, the number of line of code that you need to write is a huge amount, and also it's easy to make typical mistakes. So first of all, what we want to do is speed up the development of model structured neural network with respect to the standard deep learning framework. So commonly, from our experience, commonly we have a reducing of an average of 75% of the line that you need to write, because we embed a lot of pre-built structure. So if you like the idea of using model structured neural network to build your own network using NNodely, you can reduce a lot of the code that you need to write. Then support professionals, because when you are an engineer, when you are a physicist, a scientist in general, you are not really familiar with deep learning framework. And if you want to write, if you want to develop a very structured neural network using PyTorch, can be very hard, can be very difficult. And also you can commonly make a lot of stupid mistake when you build your data set, when you are creating your custom layer. Instead, using NNodely, many of those errors are removed from your code. So this will help you to design the network. And finally, our idea of designing NNodely was to create a repository of incremental know-how to collect example of model structured neural network. So when we are happy with a new layer, we include this new layer for using this layer in a different context. So you have a huge amount of new layers, and the community can share this new layer across the different fields, for example. Okay, so model I want to follow and help you in all the development process of a model structured neural network. So if you want to, you can scan, you can go on our GitHub page, you can download NNodely and try to use it. We have a lot of examples. So NNodely starts from the design of a model, and then we use this model that we call the neural model to build. You see that there is an arrow between the neural model and the data set. Why? Because when you structure a network, then if you have this information, you can also structure your data set. So the data set is automatically built from, for example, a CSV file, which you have your input, your output, your data, because commonly a physical system works in time, and a very standard typical file is the CSV file. So you can read the CSV file with the information of your structure, and the network and the framework will build the data set for you. Then when you have the data set and the model and the neural model, you can train the network in the third phase. Also, when you train the network, if some layer that you include inside your network needs some specific, I don't know, trick for the training, the NNodely will help you to include these tricks inside your network. One example, for example, the fear filter, so what you saw before, is commonly, we know that the inputs response will follow a negative exponential. So when you create a fear filter, automatically the fear filter is the weights of the fear filter are initialized as a negative exponential, because the filter will follow this structure. So we help the network to learn. Then after you train the model, you can validate the model. Also during the validation phase, if you are a scientist, you want to use a specific way to verify if your model is a good model. For example, in our case, sometimes we use a spectral analysis on the data, on our model. So Model I will include this additional way to verify, to validate your model that are more close to a physical understanding of your model, not just RMC or standard test that you can do with a neural network. When you validate the model, then you can compose in the phase 6. So you can compose a new model with a previous model to build on top of that a more complex model. So step by step, you can increase the complexity of your model, creating a huge model that is explainable, because you can, each block's representing something, and then you can compose in one single whole model. Then you can export. In the export also, we give you the possibility to export one single piece of the network or the whole network. Okay, go ahead, Mattia. So in this case, the modeling framework will focus in the structure of the network. So you have a lot of function and class for structure the network, input, outputs, and different relations. We have already implemented many of the standard relations. And then we have other functions that will follow for creating data, the data set, for the training, for the connection of multiple networks, for the validate the model, and final to export. Now we are supporting the standard PyTorch. So if you are familiar with PyTorch, you can build your network using Model and export in PyTorch. So then you can use your network inside your training loop using PyTorch. Or you can export into NNX. We support NNX also for recurrent network, so complex recurrent network. So that is not something that you can easily do with PyTorch. Okay, then I want to show you a nice use case that try to explain what are the main functionality of NNodely. In this case, we are modeling and control a mass spring damper, very simple physical system. So in this case, you can see a mass spring damper that is governed by a spring that have a K coefficient and a damping with C. Then you have a mass, you have a force that is applying on the mass, and you measure the position. Also in this case, we can again use the idea of finite Spunz response, because the finite Spunz response represents the free dynamics of the system. Instead, the F multiplied by the second fear along with the force, representing how the force interact with the position of the mass. So we have these two elements. Again, here we use the superimposition of forces, and we use the fear filter. So this is a very simple network structure that estimates the future position of the mass. If you take the future position and you put the future position in the loop, you can create a prediction of the mass in the future. Okay, so closing the loop, you can also define and obtain all the dynamics of your mass. If you see here, there is this neural mass spring damper that have this ice symbol on the top. This block means that is trained. So we train this block and then we freeze this block. The block gets in input only the force, okay, and the other previous position of the mass. Then we apply this force, the neural model will generate the next position, and then this next position is put back inside the list of inputs to obtain the next position of the mass as in the loop. But not only here, but also in the part related to the control, if you see there. So now we had a new network that is the neural controller that now is trained in this next phase to minimize the error between the trajectory that we want to obtain and the position of the mass that we obtain. We use here was a very simple example using a mean square error. So we want to minimize the error along this trajectory. So what we are doing during the training is train for a long sequence. Okay, so we want to minimize the error of this long sequence of future positioning And to obtain that, we are training the neural controller. So in this case, we train only the neural controller. After the train, we can extract. Yeah, please, Mattia.
Yes, it was also maybe interesting to show that here we're actually training the controller by backpropagating its gradients. So the gradients of its parameters, they're actually backpropagated through the pre-trained simulation model. So it's an example of differentiable end-to-end controller training. So it's gradient-based controller training as opposed to, of course, model-free parameter tuning approaches.
Yeah, it's true. Thanks, Mattia. Finally, I want to show you just the result. I mean, this was a very stupid example. So the network, the first plot on the top, showing that the network is able to predict exact the future position. So on the top, and the second part of the slide, you have the resulting PID applied to the system. In this case, the neural controller was just a PID, so standard proportional integral differential controller, and was able to tune the parameter of the PID to get this response. So the target trajectory are the dashed line, instead the solid lines representing the evolution of the system along the window, the span that we use for training. Okay, so then we have a more nice example of vehicle dynamics. So Mattia, if you want to continue.
Yes, indeed. So let's go to a more involved, a more complex example regarding modeling and control of vehicle dynamics. This is an example in the field of steering control for autonomous racing. So we have here an inverse dynamic problem, right? So we want to compute the steering wheel angle to be applied to our vehicle, using as input some future reference trajectory that can be given by a higher level motion planner, like a model predictive control planner. So we have this future window of desired trajectory to be tracked regarding the accelerations, the lateral, longitudinal accelerations, and vertical accelerations if we are on a 3D road, plus the vehicle velocity Vx, and these are our inputs. We have, two incremental variants of our model structural neural network for this application. We have a base version that learns the pure lateral nonlinear dynamics on a 2D road, and then an extended version that tries to incorporate the effect of the longitudinal and vertical accelerations in the calculation of the best steering angle to be applied to the car. So let's dive a little bit more deep. So let's start from how we learn the steady state of pure lateral dynamics. And to do this, we start from a well-known tool, a well-known physical tool in the classical books of vehicle dynamics, which is the handling diagram, and which basically describes the under-oversteering behavior of the vehicle as a function of the lateral acceleration. So in this case, the vehicle is understeering, especially for high lateral accelerations. And the thing is, this diagram in general has a shape that is hard to predict. It depends on the vehicle type. It depends on the performance of the tires, of the suspensions. So its shape can be hard to be modeled with a unique function. And so we propose to model it again with local neurofuzzy models. Each of the models is actually learning one part of the shape of this curve in one specific range or interval of lateral acceleration, say y. So each local branch is activated by one of these functions phi, which have indeed local support. And they are, in this case, we designed them as triangular functions that activate, so they are non-zero only in a certain range of lateral acceleration, and they activate the corresponding local neural model. And indeed, the structure of the local neural model is, in this case, a local linear model as a function of the lateral acceleration AY. And then we know actually the shape of the diagram, again, from the vehicle dynamics principles, the shape of the diagram is changing as a function of the vehicle velocity. And so we can encode this velocity dependency inside our neural approximations, our neural local models, by designing some custom speed-dependent neural functions. And we can do this quite easily, the whole process of building these local models with the custom neural functions quite easily in NNodely, in Model I. So we have a first definition of which type of function we actually want to implement. So we want to implement a local model for the handling diagram, which has at the end this expression for the output, the one that we report here. And then we define, using this function, we define a parametric function. This is a Model I object. So a parametric function is a function that contains actually learnable parameters that we can define. And then with the fuzzify command, we can easily create these activation functions phi. We can specify that they have a triangular shape. They can also have different shapes like Gaussian, rectangular, or other ones that are already implemented in the framework. And we specify their inputs, in this case, the absolute value of the lateral acceleration. And then we close the definition of the local model itself, again, with a Model I object. We pass the definition of the function, we pass the definition of the activation functions. And doing this again with a traditional machine learning framework like PyTorch TensorFlow requires a lot more lines of code. So we want to streamline the process. This is just an example for local models. And then we go, okay, this was an example for the steady state pure lateral dynamics. Okay, this is a simplified setting. In general, we have to deal with combined dynamics. So we have not only the lateral acceleration as an input, but we also have the longitudinal and vertical accelerations. And in this case, the expression of these local models is more involved. It's not a local line anymore. In this case, we design the local model. We choose to design them as a local approximation of a nonlinear double-track vehicle model, so a more complex multi-body model. We locally approximate this model around a quasi-steady state condition for the vehicle accelerations. And so we have a set of quasi-steady state conditions actually within this macro model G. And this, indeed, in this way, we can still approximate and learn the quasi-steady state combined lateral dynamics using, again, this function G, which we've seen before. And now what about the transient dynamics? So quasi-steady state means the input is evolving slowly. And this block is returning to us. So it takes as input future reference trajectory, windows of future trajectories, outputs still a window of future desired steering angles in quasi-steady state conditions. Now we can use this estimate to learn the transient combined dynamics. And we know, again, from classical vehicle dynamics theories, that the transient dynamics changes as a function of the velocity. So the vehicle may respond more rapidly at high speeds and more slowly at low speeds. And so we encode this in our design, in the design of our neural network. We have different layers, once again, finite impulse response layers, different local layers that learn the transient dynamics in different ranges of the vehicle velocity, Vx, and also vehicle accelerations in this case, because indeed we know the vehicle dynamics, the transient dynamics will change as a function of the velocity. And so at the end, we can sum the outputs of all the local models, and we have an estimate of the steering angle to be applied. We have, in this case, an additional nonlinear neural function, output function, to learn some static nonlinearities, like the steering maps, and at the end, return the steering angle to be applied at the steering wheel. So this was a more complex example. Even in this case, this part, the transient part, can be described with only 5 lines of code in Model I, again, using the fuzzify and local model functions. And more details can be found in these 2 recent papers by our group, in which we applied this controller to our full-scale autonomous race car at the Technical University of Munich. This car is actually racing this month in Abu Dhabi. And we also applied this to our F-110 small-scale cars. We can see quickly a video in which indeed our F-110 car runs on a racetrack, and we use the future windows of speed and accelerations. We use them and feed them as input to our neural network that then computes the steering angle in real time to track a given race line that we want to follow. So indeed, yeah, we use this for different applications. We have other examples in which we learn, as we've seen before, the longitudinal vehicle dynamics. So this was another example we published recently, in which we want to indeed to learn the dependency of the longitudinal acceleration AX on past windows of the brake pedal, brake or throttle pedal, the engine torque, the vehicle speed, the road slope. And we have a model-based part inside our model structure neural network. We have a model-based part, which is derived from basically from the Newton equations, from a manipulation of the Newton equations. And again, we neuralize the parts that we don't know analytically, the parts that are harder to model analytically. So in this case, the relations between the torques, the wheel torques at the front and rear axles with respect to the engine torques and brake pedal, we neuralize them with the neurofuzzy models. And then we have a data-driven part to further, let's say, fill the gaps, fill the unmodeled dynamics. This part is more generic, but still we have some knowledge inside regarding the choice of the activation functions, for example. And then we finally sum the model-based and the data-driven parts. And indeed, we have more details in this paper in which we applied this network to perform road friction-aware anti-lock braking systems. So we can actually estimate indirectly the road friction using the estimates of this neural network. Yes, and use it to enhance anti-lock braking systems. We have different examples here. I will be a bit faster. So this one was an example in which we modeled the pure longitudinal vehicle dynamics. This is instead an example in which we model the combined longitudinal dynamics. So we also have the inputs regarding the lateral dynamics, so the steering angle, the lateral accelerations. This can be used to enhance the prediction of the longitudinal accelerations. And again, we are writing a paper on this with our F110 cars. We're doing the same for the combined lateral dynamics. So not only to control the lateral dynamics, but also to learn, to model the lateral dynamics. Again, the combined lateral dynamics, so using also inputs from the longitudinal excitation and applied to the F110s. We have other applications also in steering control for autonomous parking. So we want to track autonomous parking maneuvers, and even for lateral speed estimation. So to estimate the lateral velocity of a car, which is a crucial quantity for stability systems like the ESP in modern cars. And so we have indeed a lot of examples of model structure neural networks. Gastone, if you want to shortly talk about this one, about the inverted pendulum.
Yeah, this was just a toy problem, but where we tried to do here was something little bit more complex with just a low-level controller, because what you saw before was something related to just designing a low-level controller. So someone give you the trajectory that you want to follow, and then there is the neural controller that try to minimize the error between the trajectory that you obtain and the predicted trajectory. In this case, the work was a little bit different, was trying to design a controller for the MPC, so for finding the trajectory. Okay, so in this case, the controller get the final position of the pendulum and get the initial position of the pendulum, and in this case the controller was able to find to control the trajectory of the object. It was a very simple, was a proof of concept. So also the swing up. Remember that all the training was performed using the idea of before we built the neural model, and using the neural model we built the neural controller. Then we take out the neural controller to use inside the system. In this case was nice, the last example here, because the network was able to find a non-convex solution. So something still very simple also for an MPC, but we are going in the direction to try also the policy, to find the policy of a more complex system. Okay, then we have other examples, very different from what you saw so far. So here we are designing a neural model for a 3D printing process. So in this case, we are embedding the physics of the polymerization, all the physics that govern a 3D printing process in order to probably, the objective in this case is design a digital twin of the 3D printing in order then to create a controller for the 3D printing. So the idea is I want to obtain a specific object with a specific physical characteristic. What are the parameters that I need to set in my printer to get this object? To obtain this result, we are designing, first of all, a digital twin of the printer, and then we will design a controller to control our digital twin. The next example was is an electroactive polymers. So we are designing the dynamics. We try to find the dynamics of viscoelastic material. In this case, the way that are governing the dynamics of this system are really nonlinear and complex. But also in this case, we are using some basic ideas as a superposition of forces, because here you can see that there is the force due to the elastic part. Then we have the part that is related to the viscoelastic part, and then finally the electric force. So all the three forces are combined to find the total force of the electroactive polymers. Then here was an example of pedestrian dynamics. In this case, we use what is called the social force model. That is a model that is used to predict the future position of a human. In this case, the objective is find this force that is something that is representing the movement, the direction of the pedestrian. In this case, we structure the network, mimic the idea of the social force model, and we get a nice result in training and in the prediction of the pedestrian movement. And here was an example of use Model I for something that was not something that is something that we not find, so it's a physics-informed neural network, but still we try to we implement the physics-informed neural network inside Model I. So if you are familiar with physics-informed neural network, you can use physics-informed neural network also inside Model I. So to conclude, the main advantage are, of course, with respect to the standard analytical models, are of course improved the learning potential through a custom neural blocks. Another things that are interesting stick on the analytical model is that now when you are designing when you want to design a controller for robotics, commonly at some point you need to include some not structured sensor, like a camera, LiDAR, or other sensors that are not really structured. Okay, if you are inside, or if you are already inside a framework where it's easy to manage this kind of sensor, will be much more easy to integrate this not structured network inside the same ambient, the same environment. Okay, so if you already built your structured neural network, then you can have a branch that takes the information of, for example, a camera, and structure this information out. For example, what are the position, what are the line of the lane, for example, or what is the, I don't know, the information that comes from the LiDAR sensor. So it's much more easy to integrate this kind of sensor. Instead, if you want to compare a multi-layer perceptor or general non-structured neural network against the structured neural network, we get what are the main advantage. For sure, is a better generalization to unseen data with a small training set. The focus is the small training set, because we know from the theory that if you have infinite amount of data, the use of non-structured neural network will be the best choice. And this is something that is what you do when you are working, for example, yes, with I don't know, image recognition. So you can download many images from internet, and then if your network is not able to fit the data, you increase the number of images, and it's pretty easy. But when you work with a physical system, increasing the number of the dimension of your data is much more complicated, and you need to spend money to make experiment. So in this case, embedding physics in the network is the right way, because you can reduce the number of data that you need for training. Then also another very I think very important point is the interpretability. Okay, so it's true that using a multi-layer perceptron, you can get a good results, but still you are not able to interpret the output of your network. Instead, if you create a network where each branch of the network means something, you can investigate if the network have learned correctly or not the physics. So this is another, I think, important point. As also is less sensitive to the weight initialization, because the structure of the network gives also the possibility to give additional knowledge to the network, as for example was for the field filter, where the initialization of the weights follow a negative exponential. Okay, so these were some results. So if you want, you can go on this website that is NNodely application, where we collect most of the example we saw in the presentation. There is the code and the papers if there is a paper related on these examples. These are main results we got so far from me, from Mattia, from other professors that were working using this kind of network. Yeah, we want to say something, Mattia, for conclude?
Yes, yeah. So just to conclude, yeah, I think okay. So in this presentation, we covered the topic of model structured neural networks, yeah, which indeed is a new class. Yeah, we presented as a new class of networks that try to embed indeed some prior domain knowledge in their architecture, and we proposed a framework, yeah, Model I, that eases the development of this type of neural networks, and not only. So it's in general for what we call physics-guided learning. With physical systems, so including model structured neural networks, physics-informed networks, differentiable end-to-end training of the a controller, as we've seen in the example of the pendulum and of the mass spring damper system. And indeed, in general, for rapid prototyping of these systems, even for people that are non-experts in machine learning. And we've shown different applications to some of the use cases that we are bringing forward. So yes, Gastone,
I want to conclude saying that Model I is inside is one of the main outcome of this huge grant that I got from Italian Ministry of University and Research by 1.2 million euro. And the focus of this project that will last the next 3 years will focus on the development of Model I and the development of a website that will collect the model structure neural network application. So if you use Model I to solve a specific topic, a specific problem, then you can upload your model to the website to help the scientific community to share this kind of knowledge. So it's a simple way, because I'm not mentioned, but the Model I can export also in a JSON model, in a JSON object that is representing the structure of the network. So if you want, you can share this JSON object to some other people for helping them to solve a specific problem. In particular, we will focus on autonomous system to show that this approach it works, and we will focus on vehicles, drones, and quadrupeds. If you want to give more information, you can go to my website. So try to let's apply the framework to your task and start if you like. So thank you very much for your attention.
Yes, and in general, indeed, yeah, thank you for your attention, and we're very open to collaborations. Yeah, of course, yeah, now we have a bridge between Technical University of Munich and Trento, and also other universities in Europe that are collaborating with us. So we're very open to new collaborations on these topics.
That was a wonderful talk. Thank you both again for the time. And we have a number of questions that have
Sure.
the first one is you showed an example running a controller in an F110. The question is how performant the controller is generated in this way, learned in this way, and what kind of hardware is needed if a high controller activation rate is needed.
Yes, yeah, good question. Yeah, so indeed, yeah, we didn't show too many results in this presentation. We wanted to focus more on the methodological aspect. The results are, of course, in our papers, and I can tell you in general, we can drive this type of vehicles, F110, but also the full-scale autonomous cars. We can drive them really close to the limits with these methods, and the peculiarities that we train them with just 2-3 laps of data. So we just run 2-3 laps on a track. Of course, we need this data. So this data can be human expert data collected by human experts that drive at the limits, or it can be collected with another approach that we are pursuing is to build incremental models. So we start with a baseline model. We use that to drive the vehicle. We collect new data. We train an extended version of the model, and we proceed in this way. But the amount of data is really limited, and we can push to the limits, especially in comparison with the multi-layer perceptrons, in which the performance is in general, let's say, comparable. We're not claiming that in all cases we outperform general networks, but the peculiarity is that if you train a multi-layer perceptron with this amount of data, you cannot generalize this well on new unseen data. And regarding the second part of the question, yeah, the hardware we need is actually very basic. Like on the F110, we are just running everything on our NVIDIA Jetson. On the full-scale car, we have a more powerful hardware, but actually running this type of models whose complexity is still limited does not require GPUs, for example.
No.
Of course, then, yes, if you want to.
No, I want to just to say something related to the amount of parameters. You know, if you think that multi-layer perceptron can have thousands, say 100,000 of parameters. Our network, we are talking about hundreds of parameters. So the number of amount of the parameter are less in comparison to the standard fully connected deep neural network. And with respect to an analytical model, yeah, maybe on a standard analytical model can have 10, 20 parameters. We are in the order of hundreds of parameters, but the network is still very simple. So the frequency that you can run this kind of network is very high. Yeah.
Yes.
Okay, let's go over to the next question. This goes back to the methodological part of the talk. When setting up MOLI, how do you usually decide the network architecture and activation functions? Do you follow a specific heuristics or mostly trial and error?
Yes, indeed. Yeah, this is indeed an open question. So what we do is we collect a certain number of layers that can help designers, engineers, physicists in coming up with good architectures for their application. Of course, we still need a modeling effort. So we still need to put some effort in modeling our neural network. This is something we need to do. We are the engineers that need to do that. But we provide a framework that is as flexible as possible for these needs, like to build really custom functions, custom layers, to embed indeed specific knowledge without having to create new layers in existing machine learning frameworks. So indeed, our goal is to speed up the process, collect as many examples as possible of layers that can be used in multiple applications.
Yeah,
there
for
are
example,
no yes.
now for example, we work a lot on vehicles, so we will during the project Normas that I showed you before. The idea will be, for example, build a standard model for vehicles. So you can download directly the whole vehicle model and train on your data. Maybe in some cases we can also pre-train the model, so you can download also pre-trained model for a vehicle that it can be very top layers. Then you can have a very basic layer like fear, like local model, neurophagy, and then on top of that can be, for example, motor, wheels, and then on top of that can be vehicle. So depends on which level you want to build the network, but the idea will be try to have this huge library of a different level of complexity that is able to solve specific problems. So it's true that we have no a recipe to find your model. Okay, we will try to write a publication that will help you to get with the idea of how can be a right procedure to solve your problem in general. But yeah, it's something that the scientist, the engineer need to put effort. Yeah. It's a different way to model objects. Yeah. It's a different paradigm. Yeah.
Okay, great answer. Next question. This one is a little bit more practical. How about debugging? Is it possible or useful to have the ability to shut down parts of the model to isolate others?
Yes, yeah, indeed. I think it's a good question. And I think in general, yes, like our framework is built with the idea of modularity. Yeah, so one can indeed switch on off different modules or different models themselves, which are then composed to build more complex functions. In our opinion, it is an advantage because indeed you can isolate the single contributions of different modules. Indeed, yeah, Gastone, do you want to?
Yeah, I want to say something. The idea of modeling is also to try to avoid error that comes from PyTorch. So we want to try to isolate the user from this complex neural network error. So when a neural network error will be raised by PyTorch, because our library is written in PyTorch, okay? But we will try to collect this error that comes from PyTorch and try to explain in more clear way what is your problem inside your network to help you to design a network without knowing complex framework like PyTorch. Okay, so this is, we will try to help the user also in debugging, avoiding that you get a PyTorch error. Yeah.
Okay, next one up. Any work done on using Model for robotic manipulation or grasping? That's open-ended.
This is for the future. We would really like to do that. Yeah, we haven't done it yet, but we're really looking for also collaborations to do that. Yeah, indeed, it's a very interesting application, and that would be a perfect setting, I think, also to actually apply these tools.
And also it's true that I know already some nice layers that we not design, but I saw in the scientific community looking at model structure, neural network in general. I saw that were some very nice layers that will help to model and control manipulators. So yes, the idea will be cover new additional fields. In the future, yeah. So yes, I know already that are very nice layers that can help for robotics, yeah. But we're not integrated yet, so yeah.
Yeah, contact modeling sounds like a good candidate for structural networks.
Indeed, yes.
Yeah.
That one's hard. Okay, the next one up is mine, and it kind of goes back to the beginning, to the discussion of structured versus non-structuring. Like qualitatively, I can understand how structure, how grounding the model and prior knowledge boosts sample efficiency and generalization overall. But I do wonder if you have a sort of like a quantitative sense of at what point raw scale or data scale beat that structure.
Yes, this is also
Yeah.
a very good question. By the way,
Yeah.
we will be organizing a workshop on this topic at the next ICRA 2026,
Interesting.
and the title of the workshop is exactly Data Meets Physics. So
Yeah.
at which point we need to integrate data, and where indeed instead the physics knowledge can be useful, to which extent the physics knowledge
Yeah.
can be more useful. Indeed, what we try to propose is that, at least in our experience, the best thing is to go with the physics knowledge, like with analytical physics-based models, where you have more confidence on the model, and when you know
Yeah.
the model is more accurate. Then, of course, there are certain parts that you cannot model analytically, when you have contact dynamics, when you have nonlinear tire dynamics, when you have saturation, when you have time-varying effects, temperature dependencies. And these are the parts that we want to help modeling using data. At least in our experience, this is the most sample efficient way, at least, to try to do that. But yes, this is again another open question that we want to discuss together with the rest of the community. I don't know, Gastone, if you want to add something. Yeah.
Now I'm thinking to show the picture.
Yeah, we probably have Gastone wants to show a diagram in which we have
Yeah,
from purely data driven to model based, what's in between. And there is indeed a lot of approaches in the literature, in which you try gradually to add more and more structure to the model, until, of course, you go back to.
Okay, so yeah, just to give you an idea, no? So from one side, you can have a completely data-driven. We saw from physics that 2 layers are enough to learn any function, but this is not true. So you try to add layers just without any structure. You build a multi-layer perceptron, but then you can do something more. No, you can structure a little bit more. So you can create a CNN, long short-term memory, multi-layer perceptron. You can combine all together, help attention, and you can create standard networks, so complex standard networks. On the other side, instead, you have a model-based function where all the structure of the network and also the parameters comes from physics. So you not learn anything. You just have the specific function. Oh, sorry, relation editor. So where?
Yeah, no worries. Yeah, I think we got the sense.
No,
yeah.
Yeah, but in the middle, in the between, you have a switch PDF. Okay, but in between, you have the model structure neural network. So you can decide at which level you want to integrate physics, and there is many different levels. No, so you can create some model-based networks only and combine only that, or you can combine, for example, multi-layer perceptron with a specific layer that you need. What is the point? The point is now doing that with the standard framework is not easy, and use a framework that can help you to structure this kind of network can be useful. Yeah, but yeah, we doesn't know what is exactly the best trade-off. Yeah, we don't have any answer on that.
Okay, that was answered as well. And I guess I have one last question of mine. Can you comment a little bit on the dataset pre-processing or creation step? In particular, I wonder, how do you choose which state trajectories to collect, such that when learning the neuralized blocks of your model, you actually get sensible learning? Did you do some sort of observability analysis? Does the system afford that? How do you go about that?
Yes, yeah, I think this is also related to, let's say, to more traditional system identification, if you want. So, of course, it's a matter of exploration of the domain. So we, in general, we need to be as informative as possible with the data set. This is, general rules. What we typically do with our vehicles, for example, is we start with open loop maneuvers. Like we start with the preliminary controllers. We perform like sign steer maneuvers, so maneuvers in which we perform like sign sweeps, or we steer in a certain way, or we try to combine with accelerations and braking in between. So we start with open loop maneuvers, then indeed we train preliminary versions of the model's controllers, with which we can then control and collect more data and refine iteratively like that. But in general, yes, we need to try to be as informative as possible, so to explore all the range of at least frequencies and ranges that we see during operation, even though still we have the capability to generalize beyond what we've seen during training, at least to certain extents.
Another point is when I designed, when I thought about NNodely, I thought that also the phase of creating the dataset is something that is important. I'm not developing anything about that yet, but the idea will be also, because when you design a model, okay, so you start in creating your neural model, but at that point, you already know how you navigate your space in order to learn better your parameters. Okay, because you have already the structure of the network, okay? So you have already some information that are related to their model. So one idea was to try to create some sort of controllers, okay? Some dummy controllers that can help to span the space of your system in the proper way, okay, for creating the data set. I've not investigated yet this part, but it's something that you could think about, because you have the structure of the model. So you can say, okay, I have the structure of the model. What is the best way to learn my parameters? How I can navigate the environment in order to collect the best parameter? Okay, so maybe we can think that in some way you may create some sort of controller that can help to span and collect the data for the training, but we are not working yet on that.
Great, super interesting. Okay, I guess we have a minute or two if anyone else wants to ask a question. Otherwise, I'll give back 10 minutes to everyone, especially Gastone and Mattia. Thank you guys again for the time and for this. If there are no more questions, thank you all for coming, and
thank you very much. Thank you very much.
Indeed, thanks a lot, and we're very open for connections.
Thank you very much.